Yeah, hello everyone. This week we will study this lecture will study the partial orders and the equivalence relations. So first, we just give a slightly discussion of the generation of K subsets. Recall before we studied the generation of combinations, and here we just give one algorithm to generate all K subsets. So let A1 to AR be a R subset of 1 to n, and then the first lexicographic ordering is 1, 2, 3, 4 R, and if A1 AR is different from m minus R plus 1, m minus R plus 2 all the way to n, let K be the largest integer such that AK less than n and AK plus 1 is different from each of AK plus 1 all the way to AR. Then the subset that is the immediate successor of A1 to AR is a lexicographic ordering. In the lexicographic ordering is A1, AK minus 1, AK plus 1, AK plus 2, AK plus R minus K plus 1. Okay, noted that although we here we consider only the combinations or K subsets, but the order A1 to AK is important here. Okay, because remark, for any subset of A2, let's K subset, we can arrange the element such that A1 less than A2 less than all the way less than AR, it's R subset. Okay, we can always do this arrangement, and if you look at the algorithm carefully, you will see each step we will generate a new K R subset. Sorry, let's see, this is my bad. Each new K subset, A1 prime, A2 prime, AK prime, automatically satisfy the following inequality. Satisfies this inequality. Okay, and you can search online what is other efficient ways to generate K subsets. Mathematically, this probably is useful when you do some theoretical proof. Okay, next we turn to another topic which is very important, both in graph theory and combinatorics. So it's called partial orders, and equivalence relation definition relation. Okay, actually, if you start your mathematical training from the Bourbakis idea, then the first thing you should learn before you know what is plus, what is minus, is the equivalence relation. Although it contradicts people's nature recognition of the science, but from Bourbakis' point of view, the first thing is a equivalence relation. So you should know this is very important. Okay, so let's first do the definition of the relation. Let X be a set. Consider the Cartesian product X cross X, which is just a pair of elements in X, and a subset R of the Cartesian product is called a relation on X. Okay, so any subset can be called a relation, but usually we only study some good relations. So I will explain just in a moment. It's called a relation on X. And the notation, so for A, B in X, we usually write A, R, B whenever A, B is an element of R, and A, not RB, whenever AB is not in R. For our purpose, later on, we will not use such kind of notation. Usually, later on, we will use the smaller than or equal sign to replace this R relation. But more generally, R is a correct definition. Okay, let's first look at some examples. When we choose X to be the set of all integers, and then we can define the relation R in the following way. We call A RB for all AB in X if A minus B is divided by 2. Okay, of course, you can modify 2 to any integers. Okay. And thirdly, let X be all subsets of 1, 2, all the way to n. And then we say A, RB probably I should write AB in X in front of ARB. So for all elements of X, we say ARB if A is a subset contained in B. So just a small remark, A could be just B. So AB could be the same from the definition. And fourthly, suppose X is a set of all integers, and we can define the relation just by comparing their magnitude. Okay, and this is one. As we said before, this relation can be very weird because we don't have any restriction on R. So when you define it to be less than or equal to, there will be a different relation on the set of integers. It's also possible. It's also allowed. Okay, from the definition, you see it's too weak. I mean, for the relation, you don't have any useful information. As soon as it's a subset of all pairs, it's a relation. But from reality, we would like some useful relation or interesting relation. So next, we introduce some special properties. So when R is a relation, we call R reflexive if X are X for all X in R. That means it's always, it has a relation to itself. And similarly, we have irreflexive. This is not so useful. If X not Rx for all X in R. Thirdly, symmetric. If X Y implies Y X for all XY in X. And then you have anti-symmetric. If X Y and Y X implies X equals Y for all XY in X. And the transitive, if XRY and YRZ implies XRZ for all XYZ in X. The reason we raise up such properties is because we already see them from the nature examples we list here. So if you look at that, we will see for the reflexive one, by the definition, 1, 2, 3 1, 2, 3. Let's call this as 4. This is 5. 1, 2, 3, 5 are reflexive, and then irreflexive four is irreflexive, and for symmetric, let's see, example 1, 2 is symmetric, yeah. And anti-symmetric. For anti-symmetric, we see it's 3 and 5. Actually, 4 is also anti-symmetric because there are no such x and y that x less than y and y less than x. So the condition is trivial. Okay, next for the last one, transitive. We will see that 1, 2, 3, 4, 5. All of them are transitive. Okay, so I suggest you to test the properties on the examples by yourself. And a small remark is you can define your own properties. So that's how scientists or mathematicians or computer scientists do research. They raise up correct properties to describe the phenomena we observed in nature, or raise up some structure to group together the data. So don't just be confined by the previous properties or previous definitions, and be more free to define your own. Okay, and next we are going to introduce a very useful relation, which is called partial order. So a reflexive anti-symmetric transitive relation R is called partial order. So here you have 3 assumptions: relation, reflexive, anti-symmetric, transitive. Okay, and the X together with a partial order is called a partially ordered set. Sometimes in the literature you will see they use poset to represent the same thing. The reason why we call it partial order is because we have a definition of total order in the following, and then we have an important theorem says partial order can always be embedded in some total order. So it's part of a total order. So that's why we call it partial order. Total order. So call partial order R on X total order if for all xy in X, X are Y or Y are X. In textbooks, sometimes they use the notation comparable. So every two elements can be compared. I don't like this notations, so I will not use in the following. I will try to transform it into some equivalent representations. The reason I don't like it because I think the total order is kind of put everything on the real number line, but usually the interesting phenomena we have in science multidimensional structure. They have a lot of interesting structure could not be put on a single line. So the most interesting part is the non-comparable part. Okay, just like two persons, you cannot compare them just like who gets higher GPA or who is older, who is richer. Different people have different personalities and they have different life. So I don't like the notation like a comparable. It's okay in science. Different people give different weird unlikable notations, names. So you are not expect to like all of them. Okay, next let's look at some examples. So first, suppose you have a set of n elements and fix a permutation of X, and then we can define a relation R on X by the following rule as follows. X R Y if and only if either X equals Y or X come before Y in the permutation tau. And then it is easy to verify that. R is total order. So let's do it once. Why this is true? Because first, reflexive, we always have X R X because X and X equals X. Okay, and then let's look at anti-symmetric. So suppose you have X and RY and Y are X. Then if X equals Y, we are done. Otherwise, you will have X comes, also here, comes before Y, and Y comes before X. You have contradiction. This cannot be true. So X must be Y. Okay, next, let's look at transitive. Suppose you have x r y and y r z. Okay, if x equals y or y equals z, then we always have x r z. Otherwise, x comes before y comes before z in tau, then x comes before z in tau. And then the last one is comparable. I don't want to see that. For all x, y in x, x r y or y r x. Okay. Then the conclusion is R is a total order. A remark is just in a moment we will show that actually all the total orders on a finite set can be given by such a permutation. So there's a bijection between the total orders and the permutations. So from the previous few lectures, you already have the feeling that sometimes to well understand some property, it always consists of two parts or twofold. It's always twofold. First, you need to have some concrete construction to represent it, and then you need to say that all the, for example here, all the total orders come from that construction. Okay. And I would like to make a remark to the remark that this bijection is a good understanding or a good representation. Because for total orders, we have less understanding. Usually we don't know what it is because that is because left hand side is less known, while the right hand side is way much better known. So you use some well-known objects to represent less known objects. So that will be a good understanding or good representation. And in mathematics, you can always say some bad understanding. What that mean? So usually they will give you some left-hand side and then give you some bijection to right-hand side. And the problem is both sides are hard to understood. So that's what I will call from abstract to abstract. You are doing tautologically nonsense thing. So this will be a bad representation. You will always see this result, even in some good journal papers, but I don't like that. Okay. Okay, and to give a representation of the total orders or establish the bijection, we introduce an important notation which is called minimal elements. So we call x an element of X minimal if there's no Y in X such that Y is different from X and Y are X. And here remark is, you can always, so how to say that? Okay, if you don't like R, you can use less than or equal to replace R. And then you will see clear why we call it minimal element. And a lemma is a total order or totally ordered finite set has a unique minimum element. I will not give the proof. So from, because it's finite, actually you can prove by induction. And noted that a remark. It is not true when the set is infinite. Think about when X is Z, the relation just less than or equal to, and then of course there's no minimal element. And remark 2 is, those properties can be generalized here to infinite set for generalization. Although in combinatorics on computer science, usually we deal with a finite set, but when you do some theoretical proof, probably it's better to introduce some infinite structure. To an infinite set, we need to put some subtle restrictions on the set X, like the exceeding train condition or the accessing train condition. I will not talk about that. That if you learn abstract algebra, you will meet those properties. Okay, and now, just as we said before, for partial orders, we would like to use less than or equal to symbol instead of R. So partial order is usually denoted by less than or equal for x, y in X. So more precisely, that is for x, y in X, right? X less than or equal to y if and only if x are y. And we can define a new one. So x less than y, it's not a partial order, but we can use this to indicate that x are y, less than or equal to y, and x is different from y. So be careful. Not a partial order, just a notation. If you don't want to confuse yourself or other people, you can use the right-hand side instead. There will be no ambiguity at all. Okay, lemma. So a total order on X with an element can be represented by x1 less than x2 less than xn xi in X. And if you represent it on the real number line, for example, real axis, this is exactly the comparison by the magnitude. Therefore, sometimes people call it a linearly ordered set. Okay, and here just a small remark that x1 less than x2, strictly less is not the order, not the relation, because it's not transitive. What exactly it means is x1 less than x2 less than or equal to xn, and xi is different from xj for all pairs ij between 1 and n and different. Okay, so what does this mean? This means just like you have a representation. So remark. On the left-hand side, you have some box, total order. You don't know what it is, but then by the previous theorem, you transform it to a number line. And the order just given by the comparison of magnitude. Okay. Okay, and the proof, you can look for the proof in your textbook, and I will give you the rough idea. The idea is quite easy. So take a minimal element. Actually, in this case, it's you only have a unique minimum element. Take the unique minimum element x1, and then consider x, get rid of x1. So define it to be x2. Take the minimum element x2 of the set x2, and then consider x3 defined by x2 or defined by x, get rid of x1, x2. Take the minimum x3 of the set x3. You can continue this until the last element because the set x is finite. Therefore, you have x1 less than or equal to x2 less to s3 all the way to n. And by the construction, each element is different. Okay, therefore we conclude the lemma. Next, we want to ask some similar question for partial orders. That is, can we have some geometric representation of partial orders? For the total order, we use a line to represent it. And how about the partial orders? And this is also been done, has been done by Hexan. It's called a Hexan diagram. Sorry, it might not be constructed by Hexan. Usually, that's a true fact. Usually, the theorem named after some person, that person might not be the inventor or first one who proved that, who established that theorem. It's just common fact. Okay. Anyway, it's called Hexan diagram. So we use dots to represent elements. We're connecting the dots by edges when they have relations. And another rule is that when dots are in the above, expect to greater than the ones in the below, provided they have there is a relation or there's an edge connecting them. There's a connecting edge. Okay, probably it's easy to illustrate this Hexan diagram by some example. So let's consider all the subsets of a set of 3 elements and whose relation is the inclusion relation. Then we can draw the Hexan diagram as follows. So this vertex represents the set 1, 2, 3. And this 3. One, 2. The set consisting of 1, 2, consisting of 2, 3, consisting of 1, 3. Okay, next we have 3 elements, 1, 2, 3 subset consisting of a single element, 1, 2, 3, and then the last one is the empty set. Okay, next, if we consider the relation defined by division for the set 1 to 8, then we have the following diagram. This is 8, 4, 2. and then you have 6, 3, 1. So this is 1, 3, 5, 7, 6, and then now let's connecting. So 6 has 2 edges, ending up with 2 and 3. Okay, and here actually we omit the relations between 8 and 1, 4 and 1. This is because the partial order is transitive. Therefore, as soon as you have 8 to 4, 4 to 2, 2 to 1, automatically you will have 8 to 1. And nice property is that you will see just below 1, you will have next level above, one level above elements. Those are prime numbers. Okay, next. Then we are going to prove or study the question how to embed a partial order to a total order. So can we extend a partial order to a total order? So what does extending or extension mean? So given two partial orders less than or equal to 1, less than or equal to 2 on X, the second one is called an extension of first one if X less than or equal to 1. X less than or equal to 1y implies X less than or equal to 2y for x, y in X. And an equivalent way is if we view less than or equal to 2, less than or equal to 1 as subsets, because they're relations, subsets of the Cartesian product X cross X, then the first one is a subset of second one if and only if second one is an extension of the first partial order. Of course, here we view partial orders. These two relations are partial orders. Okay, and the theorem is let less than or equal to 2 or less than or equal to be a partial order on a finite set. Oh, this is important. If it's not finite, that will be complicated. You need to use some ZFC axioms which cannot be proved. And actually, any axiom has some theorem cannot be proved, neither be proved nor disproved. This is a famous theorem of Gödel. And then for ZFC axioms, later on, Cohen proved that doesn't matter. You can assume it. All the theorem we know is still true. Yeah. If you have interest, you can look at some Wikipedia page for the Gödel and the Cohen. These two fields medalist. Okay. Let's turn back to the theorem. So here we assume X is a finite set, and then the partial order has at least one linear extension. Actually, linear extension, just some fancy way to say that, can be extended to a total order. Okay, and the idea is, if you look at previous examples, just like the Hexan diagrams, you will find the picture we have may have some degeneracy. If, for example, like, oh, that's too much. Okay, let's, for simplicity, let's just do this. And you have two green dots which cannot be compared, and two blue dots. However, for the linear order, you can collapse the graph to a line. That means each two elements can be compared. So you have degenerates. So the idea is perturb the graph to eliminate the degeneracy. This is a usual idea in physics. When you have some degenerate system, don't worry, you just put a small perturbation, add some quantity to your Hamiltonian, so that there will be no states in the same level, same energy level. Okay, so if you perturb it, then you will have the following situation. Still have the pink in front, and then you have blue one and the light blue one, slightly lower than the dark blue one, and dark blue one and light blue one, and then the red one. Okay, and then if you if you do this connection, if you add the gray one, gray edges, then you will see you have a total order, right? It's a linear, although it's quite a curve, but you can flatten it. From above to below, dark green, light green, dark blue, light blue, and red one. So that's a linear order, or the Hexan diagram for a total order. Okay, so that's a basic idea, but usually sometimes this is nice to understand, but it cannot give you actual proof. So for the proof, we use a similar idea to the one we established the linearity for the total order. So recall that for all partial orders, there's always at least one minimal element. So exists minimal element x1. Okay, so since less than or equal to 2 is a partial order. Okay, so I will leave it to you to prove this. And also, second thing is x1 is not unique in general, which contradicts the phenomena for total order. Okay, then if it's not unique, that means you have some degenerates, just like here. Let me use. Okay, just like here, you may have some degenerates. But don't worry, we just pick out one, and manually set it to be the least one, and then consider the set deleting x1. Consider set, and then there exists a minimal element x2 of this set, and then consider x, get rid of x1, x2. Then similarly, because the order is still partial order, x3 of the set. Since x is a finite set, then we can have x1, x2, x3 all the way to xn chosen as above. And in particular, noted that xi is different from xj for all 1 less than I less than j less than or equal to m. Okay, then define x1 less than or equal to x2 less than or equal to x3 less than or equal to all the way to n. Then we are done. So the last step, same as adding gray dash lines. Okay, then of course we need to prove that this is an extension. Next, we prove that okay, so this is an extension of the partial order. So prove by contradiction. Suppose that there are elements x and xj such that xi is less than xj strictly. In other words, xi less than or equal to xj, xi is different from xj. But xi is greater than xj in the order t, in the total order. So that means xi is greater than or equal to xj in the total order, and xi is different from xj. Then consider the set x get rid of x1, x2 all the way to xj minus 1. Notice that by our choice, so j is always less than I by our construction. Okay, then since xi is an element of this set, and xi less than xj, xj cannot be a minimal element of this set. Okay, this contradicts our construction, because when we take xj, we always, by our construction, we take out a minimal element. But under this assumption, xj is not minimal, so it's a contradiction. So therefore, we conclude the theorem that this less than or equal to t is an extension. Okay, next we introduce a so-called equivalence relation. It's similar to the partial order or total order, but we have a significant difference here. So we assume a relation when we call a relation an equivalence relation if it's reflexive. This is same as in the order, in the definition of order. And then you have different ones, symmetric and transitive. Recall that in the definition of order or partial orders is anti-symmetric. Okay, look at the example. So suppose you have a set of n element. X is all the subsets. And then we can define relation R as follows. ARB, so for all subsets of X, ARB if and only if they have the same cardinality. And then example 2 is a geometric equivalent relation we studied in calculus. Just think about, suppose you have vector v equals xy in R2, then we can talk about the length of the vector, which is given by square root of sum of squares. Then define a relation or equivalence relation as follows. V1 R V2 if and only if they have the same length. So geometrically, what does it mean? It means the points on the same circle centered at origin has a relation. Sorry, my bad drawing. Okay, and another example we also mentioned before. That's a division property. So for m greater than 1, define ARB such that A equivalent to B modulo M. This is always we met this in the Chinese remainder theorem kind of. So number theory. Okay, and an important theorem says that the equivalent relation gives you a partition of the set. So more precisely, let theta be an equivalence relation on X, then the distinct equivalence classes partition X into non-empty parts, and the converse is also true. So I will leave it to you to prove it. So actually here we don't assume X to be a finite set. X can be arbitrary. And what is the equivalence class? Equivalence class, for example, let's call it B. For finite set, so all the elements xi, so x let's call it bx, y in x, y is equivalent to the small x. So here is a small x, sorry. And for all different x, it's easy to see that the union of all bx, x is an element of x, is the whole set. The theorem says actually bx, you can take out some bx such that they give you a partition. Okay, I will not prove it's a kind of tautological. Okay, I would like to say the equivalence relation is very important because think about in the ancient time, long time ago, people may view one sheep, one dog, one stone one corn are different, and one sheep is more close to two sheep. One dog is closer to two dogs. One stone is closer to two stones, two corns. So originally people view these pairs are more closer. Okay, but then suddenly, I don't know when, but people say, oh no, we should define different relation, different equivalence relation. So how to define the different equivalence relation? Let's view one sheep, one dog, one stone, one corn, the same. And two sheep, two dogs, two stones, two corns are the same. Okay, then this is a fantastic invention that gives you the number, integer number, positive integer numbers, 1, 2, 3, 4. More or less, that's a starting point of mathematics. Okay, and all I want to say is you can define by the theorem we can define equivalence relations by an arbitrary partition. So you can define it in your own interest. And for example, actually we already done that in daily lives, here and there. Some people view his or her dogs closer to him or her than other people. Okay, some people view other people as more important than his or her pets. So that's actually an equivalence relation. Just we don't realize it. And in mathematics, when you say equal sign, what is equal? This is a very important question. Actually, that's some philosophers write a huge paper on defining what is yes. It's easy to say what is no, but what is yes? What is yes? A equals B, A is B. What does it mean? Okay. Next, let's look at some interesting example. Suppose you have the following permutation. In the above, we always view a permutation as some element or set, but actually, I would like to see permutations has an ample structure. If you consider all the permutations, this is a group. Describe all the symmetry. Describing symmetries of the set or the, yeah, that's it. And what is a group? That means we can define tall square as tall composed tall. This is, of course, a new permutation. So I will not define it too rigorously here, but give you some flavor. And similarly, you can define tau 3, tau 4 all the way and those act on the set 1, 2, 3, 4 to n. And then let's think about what is orbit. Orbit and tau square, tau cube, these actions. So yeah, let's at least define it for tau. So tau 1, think about this is your permutation. So we define tau 1 to be 7, tau 2 to be 5, tau 3 to be 3, tau 4 to be 2, tau 5 to be 4, tau 6 to be 1, tau 7 to be 6. And similarly, tau compose tau 1. This is tau acting out tau 1, so this is tau 7, which is 6. Okay, anyhow, actually, in some modern language, we can write tau in the following way. Parenthesis 176, parenthesis 254, and then 3. Okay, that means 1 is acting, 1 goes to, so what does this mean? That means tau 1 is 7, tau 7 is 6, tau 6 is 1. Give you a cyclic rotation. And then here tau 2 is 5, tau 5 is 4, tau 4 is 2, and tau 3 is fixed. And it's easy to see that, or if you draw a picture. So tau, you have 176, rotate, and then here you have 2, 5, 4. And here you have 3. Okay, then you will see tau square is easy to see. It's always rotate inside it, and then 1 is to 6. One is to 6, and 6 to 7. And similarly here, you have 2 is to 4. 2 goes to 4. 4 goes to 5. And 3 is still fixed. Is still fixed. Okay, then we can define the equivalence relation. The orbits give an equivalence relation. the set 1, 2, 3, 4 all the way to n. And the next example, which is just the circular permutation we studied before. The circular permutation just means just a problem like people sitting on the table and how many different position, how many different ways they can sit. And more rigorously, we define in this way. Suppose I1, let S be the set of all permutations, Sn permutations of 1, 2, 3, 4 all the way to n, and we call two permutations equivalent or has relation R if and only if exists K such that J1 to Jn can be written as Ik all the way, Ik plus 1 all the way to In, then I1 all the way to Ik minus 1. Just you cut I1 to In and some place and put the later half in front of the first half. Okay, I will stop here, and next time we will study the binomial theorems.